So hello and welcome in this advanced conduction series. So we are, as I have said earlier also, that we are already at the end of our lecture series. I will take at most 2 or 3 videos, okay, to complete this series. Now in the previous video I told you about the lumped mass analysis and when it is applicable, right? And I also started the concept of a semi-infinite body, and I have already described you the statement, the problem statement, okay, and I explained you intuitively, okay. I applied some intuitive logic and I told you, okay, I think my pencil has to be connected with the iPad. Okay, now it is connected. So I applied some intuitive logic and I told you that the time varying temperature profile will look like this. That is, at a particular time tau, it will be delta, the heat penetration depth is delta, okay, and at a particular time 2 tau, it will be delta dash, the heat penetration depth, and after a particular time it will be delta double dash. And I also have given one example of a spoon, that if you are maybe cooking something, okay, so if you have hold a spoon like this, okay, so after a I mean particular time, you will be able to feel the heat and not before that time instant, right? So now let us proceed towards the exact solution, okay. So let me tell you that these kind of problems have two types of solutions, okay. The first type is exact solution, that is for only for some fixed boundary conditions, okay. Remember, the boundary conditions has to be fixed, okay. I mean only for some fixed boundary conditions these kind of problems have exact solutions. If you change the boundary condition, then it will not have an analytical solution, okay. So it will have an exact solution and also an approximate solution, okay, and both are important. So for this I mean for this particular problem where you have the boundary condition as your, I mean this condition, that is t at x equal to 0 for any t greater than 0 is fixed at t1. For this kind of a boundary condition we do have an exact analytical solution, okay. Now you might ask that if I have exact solution, then what is the need for approximate solution? That is a very much valid question, right? But let me tell you that the complexity of the exact solution is much more than the approximate one. Now you have to see that the result obtained from the approximate solution, how much does it deviate from that of the exact solution. If the deviation is very less, like maybe 1% or 2%, even if it is 5%, then you can happily use the approximate solution, okay. So if you can get something with less effort, then you obviously will be liking that thing, right? So that is the philosophy behind the approximate solution, because as an engineer we don't give a damn about that what is the exact solution. If you can sell your thing, then you are a successful engineer, okay. That is the harsh truth. But we cannot go beyond the laws of the physics. That is why we also need to study the exact solution, okay. But again I am telling that if anyone knows the exact solution very well, okay, but if the second person can do the same thing with much lesser effort, I mean having taken some very much rigorous approximations, so those approximation can be justified, or even it can be a very naive approximation, okay. But still, if your ultimate I mean, if your ultimate result is something that is very good, then no one will ask you that, I mean, what is the physics? Okay, if you can sell your product, then you are successful engineer. That is as simple as that. So that's why we try to go for approximate things. If you go to any physicist, then he will just tell you these are crap. Okay, but we know that these are not crap. Okay, so enough talking, enough justification for the approximate solution. So now let us start. So first I will talk about the approximate solution. Okay, so the approximate solution. So now what does this mean? Let us see step by step. I will again just draw the 2D representation of the given problem. So this is our wall. Let me draw it nicely, because I feel drawing has something to do with your understanding. If I draw it like I mean anyway, you will lose your interest, right? So this is the thing, and okay, this is not straight one. Okay, fine. And this is the semi-infinite block, and I have to fix my coordinate system also. So let me fix it like this. Okay, I am sorry about that. I just need to put the internet off. Okay, otherwise unnecessary messages will come. Just give me 1 second. So this is off, and I need to also turn on the silent mode. Now it is fine. Okay, sorry about that. Now this is x equal to 0. Okay, this is x equal to 0, and this is our x axis. Clear? Okay, so I gave you a homework that you have to write the governing equation. So now I will not derive the governing equation, but I will write it directly. It will be what? Del 2t del x square, okay, is equal to 1 by alpha del t del t. Clear? So if this is our governing equation, let us see that what we can do for it. So what we will do it, we will integrate. Okay, we will integrate over x, okay, from 0 to delta. So this delta is a function of time. Okay, again we will do the same integration for this also. Now what this delta is? This delta t is heat penetration depth at time t. Now I know that you are thinking that why the hell we are integrating this. We had already a differential equation. We know something that will solve the temperature profile at each and every point, and for that we need a differential equation, right? So then why the hell we are integrating? See, the fact is, if you are approximating some profile, then at each and every point that profile will not match with the exact solution. But if you integrate the profile, then the errors will be cancelled out. So for an example, I will give you one very much valid example here. So if there is a function f that is a function of x, okay, so I will draw the exact form of this function fx like this. So this is the exact form. Okay, this is the exact form. Now I will draw the approximate thing. So this will be the approximate graph. Okay, Array. Clear? Maybe the approximate graph is something like this. Clear? Now you can see that this graph is only matching the approximate one, that is this approximate graph is only matching with the exact one at these points, at these 3 points. But if you take the integration, if you take the I mean maybe from this point, okay, from this point to maybe this point, if you take the integration, then both will have the almost same area under the curve. Okay, the difference will be very small. Why? Because at this point to this point I have this much extra, this much extra negative area, but at this position I have this much extra positive area. So this negative area will cancel out this positive area. So that is why integration always minimizes the error. Okay, and that is why we are integrating. Clear? Okay, so what this will give? So this will be your, okay, this will be your this from 0 to delta t. Clear? And that will be equal to, so 1 by alpha I can take outside, and this one 0 to delta t. Okay, okay. So now then this will be this at delta t minus this at x equal to 0, and this will be again this one only. Okay. So now see, from the boundary conditions this will be 0. I think you can understand that, because if I draw the graph of the penetration depth, that will be something like this. Okay, so at x equal to delta, it is a function of time, the slope of the graph is 0 here. See, this slope is 0. So del t del x at delta t is 0. Clear? So it is not necessary that it must be the case. Ideally this should be the case, that del t del x at x tends to I mean infinity, that is equal to 0. I mean ideally this should be the case. Okay, but if I take the boundary condition like this, then I will get del t del x at x equal to 0 is equal to 1 by alpha 0 to delta t del t del x. Okay, so now you tell me, can I take this integral, can I take this differentiation with respect to time outside the integral? Can I do this? And if your answer is yes, then write in the comment box that why you are telling so. Okay, so now we have to see the Leibniz rule. Okay, Leibniz rule for two variables. Okay, so I think you have already studied the Leibniz rule for only one variable during your n+2, and you must have studied the Leibniz rule for two variables in your B.Tech days. Okay, if you are, I mean if you are a master student or a PhD student, then you must have studied in your B.Tech days. Okay, if you have studied the engineering mathematics with a proper way. So Leibniz rule says that d dt, okay, of any function, maybe f dx, okay, So f is a function of here, I should write f is a function of x comma t. Okay, and these things are alpha t, beta t, the limits. Clear? That will be equal to, okay, del f del t, f is a function of x and t, dx, alpha beta, those are functions of time, okay, plus what? Plus f of beta t comma t into d beta dt, okay, minus f of alpha t comma t d alpha dt. Clear? So this is the Leibniz rule. Now in the fluid mechanics we have a very important theorem called Reynolds transport theorem. So if you have already studied that RTT, then you can correlate that this is the total change of any variable that can be conserved. This is the change in the control volume. This is the outgoing flux, this is the incoming flux. So we can say that RTT is a special version of this Leibniz rule. So these are the beauty of physics and mathematics. So Leibniz rule does not know fluid mechanics, okay, and neither fluid knows Leibniz rule, but they are correlated, right? So these are the beauty, okay. Now you have to develop this mentality, that is you will mug up the least amount of things, and if you can correlate different subjects, then you have to remember the least amount of things. The thing that I am teaching right now, you will study the same thing, the same approach in the boundary layer theory also. So now if you are someone that, okay, I have studied the advanced conduction, the semi-infinite domain problem, but that was totally a different thing. Now I am studying the boundary layer theory, and that is totally a different thing. If your approach is something like that, then you have to suffer, because you have to study the same thing twice. You have to mug up the same thing twice. Okay, so always try to correlate all the things, so that you have to memorize the least amount of content, right? Okay, so enough of Gyan. Now what you have to do it, just apply this Leibniz rule onto this. So I will do the same thing, copy and paste. I have that privilege, so I will do that. Okay, sorry about that. Okay, so now, okay, so I need to minimize my screen to fit it into one screen. So now what you have to do is, you will put f equals to t, okay, and here every other things are same, but alpha is equal to 0 and beta is equal to delta. So if alpha is equal to 0, so then this term is equal to 0, okay, clear. And now what is this? What is this? Okay, so only this term is equal to 0. That means if we see, then we can write for t d dt of t dx, okay, from 0 to delta, that is equal to 0 to delta del t del small t dx plus t at delta comma t into d delta dt, okay, minus 0. Clear? So we have that, okay. So what we will do is, we will replace, instead of this thing, this minus this, right, because this is equal to this minus this one. Okay, so then our equation will be minus del t del x at x equal to 0 is equal to 1 by alpha, okay, t delta comma t d delta dt, okay, sorry, minus d delta dt plus d dt of t dx 0. Okay, okay, so now this is our integrated governing equation. Let me just put a box around it. Okay, so this is the integrated governing equation. Okay, okay, fine. Now let us write the boundary conditions. Okay, so the first boundary condition is that at t at x equal to 0 for all time greater than 0 is equal to some t, what did I take, t1 or something else, t1, okay, and the initial temperature was Ti. Okay, so this is T1 and T, okay, for all x at t equal to small t equal to 0 was Ti. So this is the actually initial condition. Okay, initial condition, clear. Okay, so for time actually we need only one boundary condition because this is a single derivative in time. Okay, but for space we need more boundary conditions. Okay, so one boundary condition I have already told you, that is del t del x, okay, uh, del t del x at x equal to delta is equal to 0. Okay, that we know. So for any time we have two boundary conditions for x, that is this one and this one, and this is the initial condition. So we have completed the description of the problem. So now we will move to the solution. Okay. So now can you tell me that if I have to write this also, that T at x equal to delta, what that will be? That will be the ambient temperature, right, or the initial condition. That is, if you have hold a spoon, I mean if you are holding a spoon like this, so initially the spoon was at the ambient condition. Now the moment you put your spoon into a hot curry, then the heat will be conducted like this upwards towards the negative temperature gradient. So at any point if the heat has propagated only up to this much, then this remaining portion will be at the ambient condition, right? So that we can say. So I should write this one, but as I only want to know x equal to delta, t at x equal to delta, that will be Ti. Okay, and actually I should write these conditions in a proper manner. X equal to delta at any t greater than 0 is equal to Ti. Okay, and this also I should write as x equal to delta at any t greater than 0 is equal to 0. Clear? Okay, and one more thing. So let me write the governing equation again. Alpha into this equal to del t, right? Now in this governing equation, you put the things, okay, at x equal to 0. So at x equal to 0, what is this thing? So I have already told you that my t at x equal to 0 is fixed. It is not changing with respect to time, and that is given by this equation. That is, sorry, this equation, that is for any time small t greater than 0, after you have started your observation, your temperature is not changing, it is a constant. That means this is equal to 0. Okay, and from these two equations, this one and this one, I can directly say that my del 2 capital T del x2, okay, at x equal to 0 for any time t greater than 0 is equal to 0. So I have these 5 boundary conditions. Now this problem is not overposed, because these boundary conditions are correlated with each other. That is, saying this first boundary condition, okay, saying this first boundary condition is actually enough as saying this one. Okay. Okay, so the problem is not, I mean, overposed. Okay. Okay. But still, when you are describing something, to have the accurate description of the problem, you must say either this one or this one. Okay, according to the situation in hand. Clear? So now let us try to solve. So you see that here this thing is not equal to 0. This thing is equal to Ti from this boundary condition. But now I have already told you, you have to define your dimensionless variables in such a manner so that your problem gets simplified in the most simple manner as possible. Okay. So now let me non-dimensionalize the problem. Okay. So these types of philosophies you have to develop in your brain. Okay. So non-dimensionalization. I mean, we don't do the non-dimensionalization बस ऐसे ही हम लोग नहीं करते. There is a particular reason behind doing it. Okay. So non-dimensionalization, and the reason is nothing but to simplify the description of the problem. Okay. So non-dimensionalization is, we define theta is equal to, okay, some I mean not some t, the temperature variable, minus Ti by some T ref. Now we don't define the T ref directly, we have to find that. Okay, and we also define some tau that is equal to T by some T ref. Clear? And we also define some x bar, or maybe this time I will write some stylish variable, and that is zeta. It looks very stylish, right? But I mean, as the style comes, I mean, it is very hard to write it correctly. Okay, so x by some x reference. Okay, so here the length scale for the problem is delta, and that is time varying. So I can write this. Okay, so let me take it as x ref. Clear? So if I take it like this, so then let me do the whole thing again. Okay. So our governing equation is this one, alpha is equal to del t. But if I do the non-dimensionalization, it will become, so at this time I will skip the explanation because I have done it ample amount of times. Okay, but still I am a छोड़ो, I will tell you. That is, here in the description of theta, the non-dimensionalized variable, we have T ref in the denominator. So that T ref will be here with the into part. And here for the non-dimensionalized description of zeta, I have x reference. That is why I have to multiply x reference twice, because I was having here x square. Similarly, I have to write theta here and tau here, but I have to multiply T ref here and what else? Small T ref here. Okay. So now T ref and T ref will be cancelled out. Clear? So then this will become, okay, alpha, or I can write, okay, so what it will become, x square, x ref square by alpha T ref. So now for the sake of the simplicity of the problem, I will take this as 1. So from this equation, my x ref, okay, is correlated with alpha and T ref. Now alpha is a constant, that is a property of the material, and that will be given to you. Clear? So now you see that from the problem, what is the length scale? What is the length scale describing the problem? That is the heat penetration depth, right? So now I take my x ref of the order of the heat penetration depth. So I hope that you know this sign already. So this sign is of the order of. So I could have just loosely tell that my x ref is equal to delta. That will also suffice my purpose. But here I will say that my x ref is of the order of delta, not equal to delta. So that will be a much more appropriate description from the point of view of mathematics. So in the boundary layer theory also, we say that my y length scale is of the order of the boundary layer thickness inside the boundary layer thickness, not the outside. Okay, and loosely we can tell that my y ref is equal to delta. Clear? So if this is of the order of delta, so then here I can write this equation approximately tells that my delta square is of the order of alpha T ref. Now this T ref is what? A characteristic time scale. So this T ref is equal to your observation time. I mean, this is the representative of your observational time. So now you see that what I am getting, that is very interesting. Delta is of the order of root over of alpha T ref. That means without solving anything, I can say that my heat penetration depth will be of the order of root over of alpha into T ref. So if you only just know the alpha of the material and someone asks you that, can you tell me that how much of this spoon I will feel hot after 5 seconds? So you can give him a rough estimate. So this is the power of the order of magnitude analysis. Okay. Actually, you will study this thing in great details in fluid mechanics also, but I will not let you up to that. I will also teach you the order of magnitude analysis in this problem when I will be teaching you the exact solution of this problem. And you will study in fluid mechanics something called Stokes' first problem. So the governing equations and the boundary conditions of Stokes' first problem and that of this problem are exactly equal, just the variables are different and the solutions are also exactly equal. That is why I am telling you, don't study like that, okay, I am now studying semi-infinite domain and in the fluid mechanics I will study the Stokes' first problem. Are yaar, mathematically dono are exactly same. Try to understand this. This will just cut half of your efforts, half of your problems. Okay. So now let me again just proceed. So my non-dimensionalized governing equation is this one is equal to this, right? So I will again just keep it inside a box and I will write in a short form non-dimensionalized governing equation. So if now I write the boundary conditions quickly and obviously non-dimensionalized, okay. So the first one will be, so what it was, t at x equal to 0 for any time t greater than 0, it will be t1. So now I have to write it in terms of theta. So theta, that means theta. So theta, I mean t is what? T is theta into t ref, right? Theta into t ref. Or what I can do is directly you just put this t value into this definition of theta here, okay. So that means this says that my theta at what, xi equal to 0, zeta equal to 0. I mean just search in the net that, I mean what do we call this, xi or zeta? I think both. And tau greater than 0 is equal to t1 minus ti by t ref. This is a particular constant. And the second boundary condition, what we have what, our t at x equal to delta for any time greater than 0 is equal to ti. So that will lead me to this one. I am just changing the color because that will give me a good contrast, and that will be 0. So now you see that I have already converted a inhomogeneous equation into a homogeneous equation. So that will, and we always like the homogeneous equations for the very obvious reasons, okay. And what else do we have? Delta t delta x at x equal to delta for any time t greater than 0 is equal to 0, and this will directly give us theta, I mean del theta del xi at xi equal to 1 and tau greater than 0 is equal to 0. Clear? What else? Now why I am writing more than 3 boundary conditions? The answer of this question you will just get in the next 5 minutes, okay. So del 2t del x2 at x equal to 0 and at t greater than 0 is equal to 0. So that will boil down to this at theta equal to 0 at tau greater than 0 is equal to 0. And one more boundary condition I had, right? So what was that? What was that? That boundary condition? Initial condition. I missed the initial condition, okay. That is t at, for all x actually, infinity, okay, and at time t equal to 0 I was having ti, right. So this equation will also be a homogeneous equation. Tau equal to 0 is equal to 0. Clear? So let me see that if I can change the color of this one. Okay, I can change the color. So this one, okay, now it is fine. Okay, so these are the non-dimensional boundary condition. So again what I have to do is I have to integrate this. So can you write, okay, I will not jump any step, I will just integrate it once more, that will help you also. right? So from this step I will integrate this, but now the limit and the variable of integration, that those will be different. It will be from 0 to 1. Clear? It will be d xi from 0 to 1. So now you see both 0 and 1 are constant, so I can directly write this at 1 minus this at 0 is equal to what? I can write this one theta d psi, and all those terms will be 0. Why? Because I have this one equal to d of 0, theta is equal to 0, right? Okay. So now I know that this is equal to 0 from this boundary condition, clear? So that means this boils down to equal to this one. Okay, so here I will give you some words of caution, that see, here I had written del, but here I have written d, because the moment you integrate theta with respect to xi, then this theta previously was a function of xi and tau, but the moment you integrate this theta with respect to xi, then this is only a function of tau, not a function of xi. Then if you write here del, then that will be totally incorrect. Okay, so then this is my integrated governing equation, clear? Okay, so we have 50%, I mean we have completed the solution up till 50% more is remaining. So now the next step is you have to assume some profile. Okay, assume some profile for the temperature variation, obviously with respect to x, clear? Okay, so now then you can say that okay, I will take t equal to x. Someone will say no, that is a very naive approximation, I will take t equal to x plus b. Someone will say no, that is also a very naive approximation, I will take something like quadratic, that is something very stylish. Someone will say no, I will take a cubic. Someone will say I will take 4th order. Someone will say I will take a 50th order thing. So, and someone will say I will take e to the power x. But on which basis you are saying these things? So you have to, okay, so just focus your mind on this sentence, that you have to choose your, or you have to assume your temperature profile so that it satisfies maximum number of boundary conditions, Okay, so here I can get 5 boundary conditions, right? Actually 4 boundary conditions, because this one is the initial condition. Okay, because this one is the initial condition. So for x or for xi here I have 4 boundary conditions. So if you can say, I mean if I distort or if I change the problem description, maybe I can change the boundary condition also. Then you can have more boundary condition also. I mean more derived boundary condition. Actually this boundary condition is called a derived boundary condition. Okay, derived boundary condition, because saying this and this, I mean this one, are essentially same. So this is called a derived boundary condition. So if you can find any other derived boundary conditions, then you will have more than 4 boundary conditions for xi. So then you can have a higher degree approximation. So here we have 4 boundary conditions. So with 4 boundary conditions, you can only find 4 constants, 4 unknown constants. So in this equation, I have 2 unknown constants. In this equation, I have 3 unknown constants. In this equation, I have 4 unknown constants. So you can use any of these 3. Yes, this equation is a very nice approximation. So you can use any of these 3's because you have 4 boundary conditions. But you cannot use p equal to ax to the power 4 plus bx cube plus cx square plus dx plus e, because you don't have that much boundary conditions. Okay, so the criteria is you have to choose a temperature profile that will satisfy the maximum number of boundary condition, and there is one more criteria: it should be a feasible temperature profile. The minimum amount of physics should be obeyed. So what do I mean by that? So in boundary layer theory, you know that if this is the actual velocity profile, so if you take an assumption like this, so then you will say, okay, it is satisfying my boundary condition here and here, all the boundary conditions. No, this is not acceptable, my friend, because we physically know that there cannot be any backflow. Okay, so there are 2 conditions. So now I will be writing those 2 conditions. Okay. Okay. So to assume the temperature profile 1. So what is that? It should satisfy most of the, okay, I am saying most of the, and why I will tell that, most of the boundary conditions, and 2, it should be a feasible profile. That is, it should maintain the minimum amount of physics, or I should say in a very rough manner, common sense physics. Okay. Okay. So here for this problem particularly, I choose my theta equal to some a into xi cube, some b into xi square, some c into xi plus d. So these are my unknowns. These are my unknowns. Okay. I have to find this using that boundary conditions, those boundary conditions. So now let us do that. So what I will do is, I will just copy these boundary conditions. Okay. I will just copy this and I will paste this here. Array. Okay. So we paste this here. Okay, now it is fine. So now let us apply the equations one by one. So first I will apply this one I will apply. So what I will get? I will get my theta is equal to 0 at zeta equal to 1. So if I do that, then I will get a plus b plus c plus d. Okay, that is equal to 0. Then I will apply the second one, this one. So if I integrate the assumed profile, then I will get that 0 is equal to 3a plus 2b plus c. Okay, then I will apply this one. Okay, so here I will get, if I do the double integration, then add zeta equal to 0. So 0 is equal to, here it will be what? It will, zeta will remain. Okay, so let me, to avoid any confusion, let me write this. So it will be what? 6a into zeta plus 2b plus 0. Okay. Yes. So this at zeta equal to 0 is equal to 0. So 0 equal to 2b. So that means my b is equal to 0. So I have got one value. Clear? So if my b is equal to 0, so then I can put here 0 and here 0. Okay, so let me write these two equations. So I have now my 3a plus c equal to 0 and a plus c plus d is equal to 0. So still I am remaining with one more boundary condition, and that is this. So theta at zeta equal to 0 is equal to that constant. So if we put theta at zeta equal to 0, so then only d will remain. So d is equal to ti t1 minus ti by tref. Okay, so now when you got the d, so then you can put it here. Okay, so a plus c is equal to ti minus t1 by trf. Okay. Okay, so now you see that I can choose my tref such, that this is equal to 1. Okay, so then my definition of theta becomes, okay, definition of theta, I will now change it here and I will write it here. Tref is equal to t1 minus ti. Clear? Or ti minus t1. Okay, no, so this is equal to then minus 1. According to my definition of tref, this is equal to minus 1. I have choose my tref equal to t1 minus ti, right? T1 minus ti, yes, this one. So this is how we choose the reference variable, okay, to simplify our life. So then we have two boundary conditions, I mean two equations, two variable. This is equal to 0, a plus c is equal to minus 1, and we have d equal to what? D equal to 1. Okay, so if a plus c, now we can solve this thing, right? So I will multiply this equation by minus 1. So if I multiply this by minus 1, it will be minus, it will be minus, it will be plus. So then if I subtract this equation from this, then what I will get? I will get what? 2a is equal to 1. That means my a is equal to half. Okay, If my a is equal to half, then my c is equal to minus 3a, that is equal to minus 3 by 2. I hope that I have not committed any mistake, any silly mistake or algebraic mistake. But if you find any mistake, please tell me in the comment box. Okay. So that is the thing. So thusly I got the value of A, B was 0, C and D. So for the sake of completeness, let me just write B is equal to 0. Okay. So now can you write the theta? Theta was A into xi cube. So I should write xi cube by 2. Okay. And then what else? Plus, okay, so B is 0 and C is minus 3 by 2 xi and D is 1 plus 1. So I got this. Okay, so I got this as my theta. So now don't argue with me with the fact that my t was a function of x and time, but theta is only a function of xi here. But xi is defined as x by delta, x by x reference, which is of the order of delta. So in that delta, as this delta, I mean that delta was a function of time, or that x ref, that is my xi is equal to x by x ref. Now this x ref is of the order of delta. Now delta is a function of time. That means my x ref is also a function of time. That means my xi is a function of both x and time. Thusly, my theta or my t is also a function of x and time. Okay. So now you have got your assumed profile. Okay. Your assumed profile. So this is your assumed profile. So how much time has been covered? I can, let's say, okay, 57 minutes. Okay, still we have time. So now what you have to do is put this theta here. So firstly, I will again just copy this. This copy and paste thing has become very common, right? Okay. So firstly, I have to find this del theta del zeta at zeta equal to 0. Again, please don't forget to see that what we call these variables zeta or xi. Okay. So this at 0 from this assumed profile, you have to tell me. So this is what? This will be 3 into zeta square by 2 minus 3 by 2, okay, at zeta equal to 0, that is minus 3 by 2. Okay, so this we got. So that means now this equation will become 3 by 2, because this thing is minus 3 by 2, is equal to this 0 to 1. Now you put just this one, that is zeta cube by 2, okay, minus 3 by 2 zeta plus 1. Clear? Okay, and that we have to integrate with respect to zeta. Okay, so can you do it for me? So this one will be what? So zeta to the power 4 by 8 minus 3 by 4 into zeta square plus zeta, and I have the limit from 0 to 1, and that will be equal to okay, 1 by 8 minus 3 by 4 plus 1. Okay, so Okay, have I missed something? Have I missed something? Let me see. I think I have missed something here. Which thing I have missed? No, that is fine. I have not missed anything. Okay, so here what I can do is, no, I think I have missed something, because I should have a delta here. Okay, I should have a delta here. Okay, so what I can do is, now I can write. Okay, I mean, this explanation is totally fine. This has no, I mean, problem, but still, now I can write this zeta is equal to x by delta. Clear? That means my d zeta is equal to dx by delta. Clear? And my tau is equal to t by t ref, and that is totally fine. Okay, so this equation has no, I mean, problem. That is okay, but you can see that this is giving you 0. Okay, this is giving you 0. Because this is a mere constant, right? So what we actually should do is, okay, you can see that is, we have to use this governing equation here. Okay, so let me just copy it. Okay, so with the inertia of writing, okay, I just forgot to tell it that this equation will not work, because this is just a approximate problem, so we need to abide by the rules. Okay, so we can integrate this equation to get this, to simplify our life. Okay, but this equation will give us nothing, and that we have already seen. So we have to use this equation. Okay, so but this is still valid. This is still valid. Okay, okay, so this is still valid. We will use this one. So I will copy this. Okay, and I will paste this here. Okay, so now what was my theta? My theta was t minus ti by t1 minus ti, and that is equal to my x by delta whole cube into half minus 3 by 2 x by delta plus 1. Okay, so this exercise that we have done, this integration here to get this will not go in vain, because I have already shown you that how we reduced our governing integrated equation. Okay, so in any boundary condition, in any other boundary condition, you may have a case where delta is remaining here. So in that case, this will not be 0. Okay, so you can I mean, in that case this will not be 0. So you can have any case like that, but here we have to apply this assumed profile into this one. Now you can argue that if this is not working, then how this is working? See, you can have derived, so you could have defined it, I mean, like this, that my t is equal to some axs cube plus bx square plus cx plus d. Then you will have your a as 1 by 2 delta cube, your b as minus 3 by 2 delta, your d as, sorry, your c as minus 3 by 2 delta, and your d as 1 and your b as 0. But for the simplification of the algebra during finding this a, b, c, d, we have defined this theta and xi thing. Okay, now fine, but still we can simplify this integral. Okay, so I will show that how can we do that. Clear? So let me show you. So now if you put, so let me again copy this one. Okay, again copy and put this one. People generally don't take this much of time in solving this kind of equations, but I want you guys to understand each and every step and the philosophy behind all the steps. That is why I am taking so much time. Okay. Okay, so now from this equation, if you put here in this equation, okay, so d delta t, okay, okay, that is fine. So what we can do is, so t, let me see what, because there will be a d delta dt here. Okay, that is totally fine. There is a very good transformation here. See what I can write for this. Okay, so this is t at delta, right? Obviously at any t. Now I can write this delta as 0 to delta dx. I can write it, right? And then I can write this as dt 0 to delta dtx. Okay, I can write this. So then I will have this one as okay, so now you again see, I can put this one inside the integral, right? Then I will have minus of d dt of t, that is a function of delta and t. And why I can put this inside the integral? Because I don't need, I mean, this is a constant with respect to x, because instead of x I have written delta. This delta is a function of time, so this t is so this thing is a function of time only, not x. So that is why I can put this inside the integral. So this becomes what? Plus d dt of 0 to delta t dx. Okay. So this will be be 0 to delta t minus t delta t, okay, dx. Clear? And this we know that this is equal to our ti. Clear? And now I can also write, okay, so I will not write anything instead of this, or I can write this also as T minus Ti, okay, because Ti is just a constant at x equal to 0 is equal to 1 by alpha, okay, d dt of, so again this is T minus Ti, so that means theta into T ref, right, dx, and this also I can write as theta into T ref, okay. So this is, now this T ref is a constant, so I can cut this out from both the sides. So now this becomes theta at x equal to 0 is equal to this one. Clear? Okay. So now this you can find, and you can also write del theta del xi, just you have to ensure that this is I equal to 0 and you have to write here delta, 1 by delta, that is equal to 1 by alpha d dt. Now you can just write here d xi, okay. Now you have written as xi, so you have to multiply 1 alpha, sorry 1 delta. Now delta is not a function of xi or x, so you can take it out, but then this limit will be this. Have you understood? That is, what I have done is this x is equal to what, xi into delta, but delta is not a function of x, so then I can take it out, okay. So it has become like this, okay. So now this is what, this we already got as minus 3 by 2, right? Here we already got as minus 3 by 2. Yes, here we got as minus 3 by 2. So here I will write minus 3 by 2 delta is equal to 1 by alpha, okay. Now d delta dt, now this integral we have already found out, okay. So at least all these things will not go in vain. So this integral is this, that we have already found out, okay. This integral is this, clear, and that is this one. So this one is what, this one, that is this one is our 1 minus 6 plus 8, so that will be 3 by 8 if I am not doing any mistake, okay. So 3 by 8, so this will be your into 3 by 8, okay, into 3 by 8, this is just 3 by 8, okay. So I can cancel out this 3, this will be 4, okay. So then I can have 1 by delta is 1 by alpha d alpha dt, I can write this 4 here, okay. Okay, so this will be plus 3 by 2, right? We got that because this was minus 3 by 2, right? This thing was minus 3 by 2, okay. So then I can now directly integrate 4, okay. So let me write it, delta d delta is equal to 4 alpha dt, then I can integrate it, this one is equal to 4 alpha dt integral, okay. Now that means this will be delta square by 2 is equal to 4 alpha t plus c. Now at time t equal to 0, there was no penetration depth. Now my battery is running out, so I have to end it soon. At time t equal to 0, there was no penetration depth. That means at time t equal to 0, this will be equal to 0. That means my C is equal to 0. Now you see I have got delta square is equal to 8 alpha t. So that means my delta is equal to root over of 8 alpha t. See, we already got that my delta is of the order of root over of alpha into t, but here we got the exact constant also. Here we got this exact constant 8 also. Okay, so that was the power of order of magnitude analysis. So this is, I mean, not doing anything, just by some common sense, we could tell that this is of the order of alpha delta t. But now we got that constant, and that constant is root over of 8. We got that. Okay, but this is also approximate. This is not exact solution. Okay, this is approximate. So the moment you get this delta, okay, then you can get your T, the temperature profile. Okay, because you already have assumed your temperature profile like this. You already have assumed, or let me show the, yes, this part. So this is your temperature profile. You know that my temperature profile is a function of x. So in this assumed temperature profile, only this delta was unknown, only the form of delta was unknown. Now you have already got that my delta is root over of 8 delta t. So now if you put this as root over of 8 delta t, then you got the whole approximate solution. So this is your answer. This is your approximate temperature profile. Okay, so with this I will end our approximate solution, and I really apologize to you because this part was not necessary. So let me make a brief recap that what we have done. So firstly, you have to integrate your actual governing equation. Okay, you integrate your actual governing equation and apply the Leibniz rule. So you have to integrate your actual governing equation, this part, then you apply the Leibniz rule to get this form, and this form you have to take this d dt outside the integral. In other words, you have to get the average temperature. So this thing is kind of an average temperature. Okay, so you have to get this form. Okay, and why we are integrating, that I have already told. Okay, to smooth out the errors. Then we define the most amount of boundary conditions that we can say. So I have also said that this is a derived boundary condition. Okay, then now we need to non-dimensionalization for only one purpose. And what is that purpose? So okay, that purpose is we have to assume some profile. So you can, I have told you already, you can assume some profile like t equal to some t equal to ax cube plus bx square plus cx plus d. But then finding this a b c d will be a bit difficult, because this a b c d will not only be a function of some number, but it will be a function of delta also. So then you will get your a as 1 by 2 delta cube, c as minus 3 by 2 delta, d as plus 1. Okay, so rather we just want to work with numbers. That is why what we do is we define theta is equal to some t minus ti by t1 minus ti. And why t1 minus ti? To make this number 1, to make this number 1 in this boundary condition, to make this number 1 in this boundary condition. Clear? So first step is integrate your governing equation, apply the Leibniz rule. Okay, and after the Leibniz rule also, you have to apply this one here, this step here, and this is your final form. Okay, and this is your final form in terms of the non-dimensionalized variable. Sorry, this one is your final form in terms of the non-dimensionalized variable. Okay, so I am again just repeating, that is, okay, so now the battery is 10%. I have to wrap it up. So you have to integrate the governing equation, and okay, you have to apply the Leibniz rule, and this is the non-dimensionalized governing equation. After that, you define your non-dimensionalized, okay, sorry, this was the dimensionalized governing equation. After that, you define your non-dimensionalized temperature for the purpose of finding the constant A, B, C, D easily. So you define theta and psi and tau. So tau does not matter here. Okay, you just define theta and psi, and you get your temperature profile like this. That is fine. Now the moment you got your temperature profile, you just put that temperature profile into your integrated governing equation. Now here I have converted this dimensional governing equation into its non-dimensional form, but see, this T is here not converted into tau. Okay, this T here is not converted into tau. So what is converted, that is only this x is converted into xi and this t is converted into theta. So the moment you do that, then you will get, now you put the expression for theta here and here, then you will get this expression. After that, you have to just integrate to get the delta as a function of time. This was the step, and in whole this step, this is not necessary, that you don't have to integrate the non-dimensionalized equation. Okay, then you will not get anything. So you don't have to integrate the non-dimensionalized equation. I am really sorry for that. I mean, I don't have any shame to say these things, because I did not have any practice just before teaching you. I just studied all these things 1 year ago. So that is why I just forgot that I will not get anything by integrating the governing equation. But anyways, now we have understood, and this is okay. I mean, I don't have any shame by doing some mistakes while I am teaching. And you must also understand that I am no one very high. I mean, I am not here and you are here. We all are at the same level. Okay, that's why I can also commit mistakes. Okay, so from these things, you should accept the fact that this person who is teaching us is not different from us. It is not the fact that he knows a lot and we don't know anything. Okay, so we will learn all the things together. Okay. So with that, I would like to end today's lecture, but just for one last 5 minutes, I will just take 5 minutes to tell you. Okay, this was the mid-semester question. Okay, so this was the mid-semester question. You see this problem: a semi-infinite solid having thermal diffusivity alpha and thermal conductivity K at ambient temperature. This is the ambient temperature as well as your initial condition, is suddenly subjected to a uniform and constant heat flux Q naught. So now here the boundary condition is not this is equal to T1, but the boundary condition is del T del X at x equal to 0 at any time t greater than 0 is equal to minus Q1 by K. This is your boundary condition that is given. Okay, and see, the first question is write down the transient governing equation in dimensionless form with appropriate boundary conditions. This you can do now. Show that the instantaneous temperature profile can be expressed as this. To do that, you have to go through all this exercise. That is, here this t, here this t is shown as your 1 minus x by delta whole square. That means this is a quadratic form. So you have to take t equal to ax square plus bx plus c. You have to find this a, b and c, and you will see that your t will be something like this. Your t will be something like this. You can put your t in this form and set up the integral equation for the heat transfer, set up the integral equation for the heat transfer. So that means you have to integrate the actual boundary condition, not the non-dimensionalized. Okay. For the problem and solve for the heat penetration depth delta T. Okay, find the temperature profile Tx in dimensionless form. So, okay, if I get time, then I will solve this problem also, but this is your homework. The only difference is that you are told that you have to assume a quadratic form, not a cubic form. It is told that you have to assume a quadratic form. Okay, so you have to do that. You assume t minus t infinity, okay, that is equal, and by some maybe t ref, that is equal to ax square plus bx plus c. Then you have to find this a, b and c. Then you will see that ultimately it will boil down to 1 minus x by delta whole square. This is your homework, okay. And another difference is the gradient at x equal to 0 is given, not the exact value. So this is a Neumann boundary condition, not a Dirichlet boundary condition. Clear? So again, if I get time, then I will solve this one also, but I will do the exact solution of the problem that I have already described you. After that I can do this, okay. But before that you must try it and write in the comment box that if you are successful to solve this problem or not, okay. So we will meet in the next video. Up till that, goodbye, take care and thank you.